Okay, so basically, I proved the statement. Why mathematical induction is, a legit thing. As to say, right? So we learned that if we have a statement for every natural number, right? So if Pn is a statement for every natural number, uh, if the initial case is true, and then also if we can prove that the previous case implies the next case, then that's basically how you prove that a statement is going to be true from there on and after, right? Again, usually the original in proof of induction is that you start with the first statement P1, and then you prove that PK implies PK plus 1, right? Then the one variation I showed is that, okay, maybe it's not, maybe the statement is not right from the get-go, but once you reach to some number L, right, then you can say, okay, for K greater than or equal to L, PL is true, but also PK will imply PK plus 1, right? And I guess this one too, right? Because so technically when you learn proof by induction, even though the proof says, the theorem says, okay, just check that P1 is true, or check that the initial case is true, right? Well, technically speaking, if you have something that you want to prove, you probably want to check more than the first case, right? You probably want to check the first, the second, the third, up until some point, right? So that's why this other variation of on the theorem is it's kind of valid, right? If not only you assume that PK is true, but also you assume that every P1, P2, P3 up until PK is true, then if you can assume that all these are true, prove that PK plus 1 is true. So I'm going to show an example basically for each case, one for like, a statement that's true all the time. I'm going to show you a case where like it's just true after some specific point. I'm going to show you a statement in which you do need not just to know PK, but some previous ones as well. And I do want to do a fourth example. That being said, I'm just going off. I'm going a cappella. I don't know what's gonna go, so I don't know if this is gonna end up being one video or two, because I always take a long time explaining stuff, right? So anyways, so that's what this video, and I don't know if the next one will be the same, right? So examples of proof by induction. Examples of proofs by induction, I guess. Mathematical induction. Alright. Okay, well, the first statement is actually a very famous one. Here's the statement. So my statement Pn is gonna be that if you add 1 plus 2 plus 3, plus 4 plus 5, up until a specific end, right? Number, right? So 1 plus 2 plus 3 all the way to like 7 or something, right? So if you add the consecutive numbers from beginning at 1 and ending at n, this sum will always be equal to n times n plus 1 divided by 2. So this is a statement, right? For whether n equals 1, n equals 2, n equals 3, n equals anything, this is a statement, right? It's only going to be either true or false. Well, by the way, so what's P1? P1 would just mean that you start at 1, right? But then if n equals 1, that means that you end at 1, meaning that actually on the left side of this equation, it's an equation as you can see, right? Then we just have 1, right? Because you start at 1, but then if n equals 1, you end at 1, then it's just that. And then on the right side, you have 1 plus 1 over 2. So is this statement true or false? Is 1 equal to 1 times 1 plus 1 over 2? Well, this is equal to 1 times 2, basically. So 1 times 2 over 2, yeah, it's going to be 1, right? It checks out. What would P2 be? Let's just, by the way. So P2 would mean, let me do it below. P2 means that, again, you start at 1, but then you're going to end at 2, right? So that just means 1 plus 2. So P2 equals 1 plus 2 equals 2 plus 1 divided by 2. So what's 2 plus 1 divided by 2? Well, I guess these two are going to cancel, and 2 plus 1 is 3, right? 3 over 1, which is 3. 1 plus 2 is 3. Again, it checks out, right? So again, when you first learn proof by induction, they don't just tell you, okay, check that P1 is 2. They'll tell you, check that a couple of them are true. What about P3? Is P3 true? So P3 would mean 1 plus 2 plus 3. Again, you end that n. So is 1 plus 2 plus 3 equal to 3? 3 plus 1 over 2. Right? Well, this is 3. 3 plus 1 is 4. So 3 times 4 divided by 2. 3 times 4 will be 12. 12 divided by 2 is 6. So is 1 plus 2 plus 3 equal to 6? Oh my gosh, right? So, you know, if it works 3 times, it looks like it's going to work, you know, for all natural numbers, right? Well, how do we actually prove that? That's what we're going to use induction. Let me just do one more on the side, because I feel like I have space over here, right? So, again, technically, you will want to prove, you want to, I mean, if at any point it fails, if, you know, if it already worked for 1, and then sometime later it doesn't work anymore, then that's your counterexample, meaning that you probably won't be able to prove this by induction because the statement will be false, right? Alright, so P4, I just want to do it one more time. So it means that we start at 1 but end at 4, right? So 1 plus 2 plus 3 plus 4. Is this thing equal to 4 times 5 over 2? 5 times 4 is 20. 20 over 2 is 10. Is 1 plus 2 plus 3 plus 4 equals 10? Yeah, right? Alright, so not only have we proved, so basically for our proof by induction says, okay, prove it for P1. Well, we did. Not only did we prove it for P1, we actually went overboard. We proved it for P1, P2, P3, P4. Okay. Now, so basically that's the part A of the proof, right? The part B is now to prove the following. Suppose we know that PK is true. Prove PK plus 1 is true. Right? Alright, so suppose PK is true, prove that PK plus 1 is true. So we're going to assume, so now we're doing a proof, a mini proof. So assume that PK is true. What does that mean? It means that 1, okay, so 1 plus 2 plus 3 up until K, right? This has to be equal to K plus 1 over 2. Okay, what do we want to prove, right? Let me put this on the side. So I'm gonna put this in a bubble, meaning that this is not part of the proof. This is more like me thinking out loud, right? So I want to prove PK plus 1 is true, right? What is PK plus 1, right? PK plus 1, maybe I should use blue instead. Oh, sorry. Just give me so PK plus 1 is a statement. What's the statement? That 1 plus 2 plus 3 up until K plus 1 equals, right? So our statement, I guess I should maybe like highlight it or something, right? This is our original statement, right? This one right here. So when I say PK plus 1 is true, I'm just saying I'm gonna substitute K plus 1 for the n, right? So where do you see an n? You see an n there, there, and there. So PK plus 1, the statement PK plus 1 is saying that 1 plus 2 plus 3 up until K plus 1 should equal K plus 1 times K plus 1 plus 1 over 2. So really, what I want to prove, I want to show that 1 plus 2 plus 3 up until k plus 1 equals k plus 1, k plus 2 divided by 2. This is what I want to show really. If I can show that that's true, a true statement, then that's the end, right? Right now, I only have that 1 plus 2 plus 3 up until k equals k times k plus 1 over 2. I want to show that 1 plus 2 plus 3 up until k plus 1 equals k plus 1, k plus 2 over 2. I know it might be blurry, but that's why I'm saying it out loud, right? Well, so how do I use this information to prove this statement? Well, the thing is that 1 plus 2 plus 3 up until k plus 1, well, what's the number before k plus 1? The number before k plus 1 should be k, right? So what I'm saying is that maybe I can, there's a whole different ways of proving this, right? How do I prove this statement? Well, I can do it, for example, this way. Then consider, I know, the left hand side. So people should write left hand side, right? So 1 plus 2 plus 3 up until k plus 1, right? But before k plus 1 is k, right? So really, when I say 1 plus 2 plus 3 up until k plus 1, if I really read the whole list out loud, obviously 1 plus 2 plus 3 plus 4, blah, 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 and then k minus 1, then k plus 1, right? So 1 plus 2 plus 3 up until k plus 1 equals basically 1 plus 2 plus 3 up until k, right? And then the k plus 1. So why am I making this distinction? Because I'm assuming that pk is true, meaning I'm assuming that 1 plus 2 plus 3 up until k equals this. So I'm going to substitute 1 plus 2 plus 3 up until k for k plus 1 over 2, right? So then this equals k plus 1 over 2, but then plus a k plus 1. Okay, alright. Well, I have a fraction here and like what looks to be a whole number. So what can I do? Well, I need to make this into a fraction, right? How do I make it into a fraction? Multiply by 1, right? So this k plus 1, I'm gonna divide by 2, but then multiply by 2. So why do I want to do that? Because now I have two fractions whose denominator is 2, meaning that now I can combine them. So this is equal to k plus 1 plus 2 k plus 1, everything divided by 2. Alright, I mean, looks like all you have to do at this point is just algebra. K times k plus 1 is k squared plus k. And then 2 times k plus 1 is going to be 2k plus 2. So we have k squared plus k plus 2k plus 2. And I mean, we can only combine like terms at this moment. So we have k squared plus 3k plus 2 over 2. Right? So we started with the left hand side, 1 plus 2 plus 3 all the way until k plus 1. But then we cut it short on this side so we can use our induction hypotheses. And by using our induction hypothesis, we will get to substitute this for just that. Then the rest is just algebra, right? And we end up right here. K squared plus 3k plus 2 over 2. I want this to be equal to k plus 1, k plus 2 over 2. Well, if you can smell where this is going, I'm assuming that if you're good at factoring, this thing somehow factors into k plus 1, k plus 2 over 2. Does it? Well, I mean, I don't know. Saying that this factors into that is also the same thing as me asking you. If you multiply k plus 1 times k plus 2, do you get k squared plus 3k plus 2? And I'm sure that the answer is going to be yeah. Right? So that was it, right? First, we proved the statement Pn, right? We showed that the first condition is true, that P1 was true. Well, actually, we showed that it was P1, P2, P3, and P4 were true, right? But for the proof itself, we only needed to show that P1 is true. And then the second condition, suppose that pk is true, prove that pk plus 1 is true. Well, we did it, right? If we assume that pk is true, then we know we can assume that we can use this thing. And then we have to ask ourselves, how do we prove pk plus 1? Well, pk plus 1, you have to like say out loud what that is, right? In this case, it was 1 plus 2 plus 3 up until k plus 1 to be equal to k plus 1 plus 1 over 2, which is why it's k plus 1 k plus 2 over 2, right? And then, yeah, right, we start with the left-hand side, right? So this is the statement we want to prove. This equals that. And by left-hand side, I mean we start with the left-hand side, and we did a bunch of algebra to show that we end up with the right-hand side. So left-hand side equals right-hand side. And yeah, I would say that that's good enough to say that we approve the statement, right? So I really want to talk more about this, because if you think, okay, who came up with this, right? I do want to touch a little bit with the history. Who could have possibly came up with this observation, right? Well, it was actually a kid back in the I think the 1800s. I don't know if it was. I don't know if it may have to be maybe late 1700s. I'm not too sure. Some kid named Gauss, and basically he's one of the definitely top two most skillful mathematicians, I suppose, right? I mean, that's a weird thing to say, because I'm sure nowadays, people, mathematicians today know, more than Gauss, I suppose. But honestly, we only know it because of Gauss. He was a genius. And again, this really shows that he was a genius. When he was a kid, I think the story goes that the teacher was going to punish him. Hey, if you misbehave, I'm going to assign you this problem of tell me what's 1 plus 2 plus 3 all the way to 100, right? So supposedly back in those days, yeah, imagine having to add all this up. Probably it will take you all summer, maybe, right? Well, Gauss didn't look at this problem as a punishment. Gauss looked at this as, hey, I want to know what that is. So story goes that he noticed something. Say that x equals 1 plus 2 plus 3 all the way to 100, right? Well, he noticed that, look what happens when you write it backwards, right? So that same amount, x, right? 100 plus 99 plus 98, and then you go all the other one to 3 plus 2 plus 1, right? Well, 100 plus 1 is 101. But then 99 plus 2 is also 101. 98 plus 3 is also 101. So basically, if you add them in this way, you're just getting 101s, right? So x plus x equals 101 plus 101. It's 101 how many times, right? Well, it's 1, 2, 3 all the way to 100. So basically 2x equals 101 100 times. So 2x equals 101 times 100. So x equals 101 times 100 divided by 2, which will be 101 times 50, which will be 5,050, right? So basically he came up with the formula because he was trying to generalize this problem, I mean, if you switch 100 for n, so you have 1 plus 2 plus 3 all the way to n, and then suppose that you write it backwards now, so you have n plus n minus 1 plus n minus 2, and again, right? So n plus 1 equals n plus 1, sure, but n minus 1 plus 2 also equals n plus 1. N minus 2 plus 3 will, again, n minus 2 plus 3, again, n plus 1. So in his generalization, he noticed he had n plus 1 plus n plus 1 plus n plus 1. How many times? N times, right? Let me just write it all here. So x equals 1 plus 2 plus 3 all the way to n. Write it again, but now backwards, n plus n minus 1, because that's the number before n is n minus 1, right? Can we all agree on that? And what's the number before n minus 1? Maybe n minus 2, right? And what did he say? Okay, so then add them up. X plus x will be n plus 1 plus another n plus 1 plus another n plus 1, right? And how many n plus 1s would you have? You would have n plus 1s n times, right? So 2x equals, yeah, right? So 2x equals n plus 1, how many times? N times. So if 2x equals n plus 1 times n, that means that x divided by 2 on both sides, x has to equal n plus 1 over 2. But what was x to begin with? X was 1 plus 2 plus 3 all the way to n, right? So 1 plus 2 plus 3 all the way to a specific n should equal n plus 1 over 2. Now you might be thinking, okay, well, why isn't this a proof? You know, why not claim this proof? Well, I mean, I think so. Again, a proof is just a convincing argument, I suppose, and you could say that everything shown here is convincing. That being said, I'll tell you this: it probably isn't. Even if it's convincing, it might not be considered rigorous. You know, mathematicians. You know, if you become a mathematician, if you get a bachelor's and master's in math, yeah, it's going to be expected of you to be able to produce a rigorous proof. So even though all of this is beautiful, I would say, you know, if you really want to prove this statement in a rigorous manner, you would have to use induction. I would say here's a weird thing, right? We have n plus 1 here, n plus 1, and I'm claiming that this is n times, right? Well, I'll just keep it short. Anytime you're doing math and you have to say the argument n times, that's a big hint that you probably should use a proof by induction to be able to claim you have a rigorous proof. So I'm just gonna say that, you know, maybe keep that in your mind. Anytime you're doing some math and you have to use the argument, oh, well, I have this thing n times, that probably means you should do a proof by induction. So okay, so pros and cons. Maybe the con about proof by induction is that, you know, you can do a proof by induction, prove it, but you probably wouldn't know this whole story, right? So you might feel unsatisfied. You know, if someone just gives you a statement and they tell you prove it, yeah, you can prove it with a proof by induction, but you might feel like, well, I don't really know who came up with this, right? So the thing is, again, pros and cons, right? Imagine you would have said, okay, forget about 1 plus 2 plus 3. What if I just want to add odd numbers, right? So 1 plus 3, 1 plus 3 plus 5, 1 plus 3 plus 5 plus 7, right? What are there's just one more. Suppose that you just want to do odd numbers, and you notice a pattern. Okay, 1 is just 1, sure, whatever. 1 plus 3 is 4. 1 plus 3 plus 5, well, 1 plus 3 is 4, plus 5 is 9. 1 plus 3 plus 5 plus 7, well, 1 plus 3 plus 5 was 9. 9 plus 7 is going to be 16. 1 plus 3 plus, so 16 plus 9, 25. Do you guys see a pattern? You know, this is P1, this is P2, P3, P4, and P5, right? Do you guys see a pattern? Yeah, right? I mean, it looks like the sum of odd numbers, of consecutive odd numbers, they turn out to be equal to perfect squares. Not just perfect squares, you know, consecutive perfect squares. This is 1 square, this is 2 square, 3 square, 4 square, and then 5 square. So then maybe you can come up with this statement, right? The way that you would write it will be this. Pn, the statement Pn will be 1 plus 3 plus 5 up until, well, if I want this to match, this thing has to be 2n minus 1. If I want it to match, right? If n equals 1, 2 times 1 minus 1 is 1, right? So that would mean that you start at 1 but you end at 1. That's why we only have 1. Suppose 2, n equals 2. 2 times 2 is 4, minus 1 is 3, meaning that you start at 1 and you end at 3. Well, that's that, right? If n equals 3, again, 2 times 3 is 6, minus 1 is 5, so 1 plus 3 plus 5, right? You start at 1 and you end at 5. So this will be the most appropriate way to write this statement that we're looking at. And according to this, if you see the pattern 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 squared, this should be equal to n squared, right? So this is my statement, Pn, 1 plus 2 plus 3, so all the odd numbers up until 2n minus 1 equals n squared. And this is going to be true for all n in the natural numbers. Alright, so here's the statement. Suppose that you came up with the statement just because you notice a pattern, right? Maybe you don't have a cool explanation like we did here, but suppose that you notice a pattern and then you come up with a statement. Well, if you wanted to prove that it's true, you have the tool necessary, right? You have proof by induction. You can apply proof by induction and then check if this is actually true, right? That's the power of proof by induction, is that you have a statement that relates to the natural numbers, you can prove it. You might not be satisfied, you might be looking, man, I want a bigger picture. You know what? Sometimes in mathematics, this is as good as it gets, that you see a pattern and that you can prove the pattern. Hey, that's pretty cool, Like, at least you know that this pattern will keep holding. This pattern will continue to be true infinitely many times. You have the peace of mind to know that. So again, pros and cons, This, you might feel like, okay, coming up with a formula like this is way cooler thinking like this. But technically speaking, if you use proof by induction to prove this statement, you've done it, you did your job. You proved that it is indeed a true statement. Alright, so again, to let you guys practice with proof by induction, I'll let you guys prove this one because again, I want to get to more examples, right? Okay, I'm looking at the time, and I guess this will be a two-parter because again, I definitely want to get to the example where, like, a statement is not true right away, but eventually it is. And I also want to prove a statement in which you definitely need not just PK, but P1, P2, P3 up until PK. So I'll just leave it here. I'll go easy on you guys. So again, if you guys want to keep seeing stuff like this, leave a like or leave a comment if you have any suggestions. I do want to eventually do like a stream maybe where I take questions. If you guys have math questions, just ask them to me. But alright, again, I don't want to have a gigantic video, so this is going to be just part 1, and I'll see you in the next one.